Ever wondered what makes clusters so important in data mining? Well, let's unravel this mystery together. Clusters are like the secret ingredients in a recipe, the magic that organizes our vast data into meaningful, digestible chunks. They're like the librarians of data science, categorizing and enhancing efficiency. They make the daunting world of data mining much more manageable and precise. So, are you ready to explore this fascinating world of clusters? Stay tuned as we delve deeper into the different types of clusters and their specific roles. First up, we have centroid clusters, but what exactly are they? You might think of a centroid as the center of something, and you'd be right. In the realm of data mining, centroid clusters form around a central object or centroid. Imagine a bustling city. The city center with its skyscrapers and landmarks is the centroid, and the surrounding areas are the cluster that forms around it. Centroid clusters are not just theoretical concepts, they're the backbone of many clustering algorithms. Take k-means clustering, for instance. This algorithm partitions data into k distinct clusters based on distance to the centroid of that cluster. Hierarchical clustering, on the other hand, creates a tree of clusters, with the centroid being the root of each cluster's subtree. These algorithms, and others like them, are used in everything from customer segmentation to image recognition. So, centroid clusters, the foundation of many clustering algorithms, help us identify the core of a cluster. Next, we have distribution clusters, a different beast altogether. These clusters are not as straightforward as centroid clusters. They're formed based on the statistical distribution of objects, rather than the physical proximity of data points. Imagine a group of data points scattered in a particular pattern. By analyzing this pattern, we can determine the likelihood of a data point belonging to a certain cluster. This is where methods like expectation maximization come into play. Expectation maximization is a statistical technique that estimates the probability distribution parameters of a dataset. It's like playing a game of guesswork, where we iteratively estimate and maximize the likelihood of the parameters until we reach a point of convergence. These clusters are particularly useful in scenarios where data distribution is more important than data proximity. They let us gain insights into the spread of data points, helping us understand patterns, trends, and even anomalies. In a nutshell, distribution clusters help us understand the spread of data points. Lastly, but certainly not least, we have density clusters, a concept that, as the name suggests, revolves around the density of data points. Density clusters are formed when we have a high concentration of data points in a particular region. Picture a bustling city center, where the density of people is much higher than in the surrounding suburbs. That's essentially what a density cluster is in the world of data. These clusters are incredibly useful in algorithms like dbScan and optics. dbScan, or density-based spatial clustering of applications with noise, uses the concept of density reachability to form clusters. Optics, on the other hand, orders the data points such that spatially closer points become neighbors in the ordering. This makes it possible to extract density clusters of varying shapes and sizes, which can be a real game changer in data mining. Density clusters, therefore, help us identify clusters based on the closeness of data points. Now that we've explored the different types of clusters, it's time to connect the dots. Let's take a step back and revisit the essentials. To start off, we delved into centroid clusters, the ones that group data using the proximity to central points. The key takeaway? These clusters are great for scenarios where the distance between data points is a critical factor. Moving on, we dived into the world of distribution clusters. These clusters, remember, are based on statistical distributions. They're particularly useful when you're dealing with data that naturally falls into certain distributions or patterns. Our exploration wouldn't have been complete without density clusters. These clusters find dense regions in the data space where there are many closely packed data points. The benefit? It's ideal for identifying shapes and structures within your data that might not be visible otherwise. So why does all this matter? Understanding these clusters is fundamental to effective data mining. It's not just about identifying patterns, but also about making sense of large and complex datasets. Each cluster type has its strengths and is suited for different kinds of data and scenarios, but don't stop here. The world of data mining is vast and ever-evolving. There are more clustering techniques to discover, each with its own unique approach and perspective. Remember, a solid grasp of clusters will empower you to unlock the full potential of your data mining pursuits. So keep exploring, keep learning,